Okay, so we here in Rstudio to give yet another example on simulations. This time a little more difficult one. It's the famous greenhouse experiment that we're now following up for a couple of weeks. Um, so this is like I said, quite complex one. So I hope you have been doing the most straightforward examples given in the markdowns. Remember, the greenhouse experiment is about two soils, fertile or rich and poor, and we're going to see whether whether maize plants make more phytochrome A in these soils. We have a greenhouse with three tables. On each of these tables, we have put one variety. Each table we split into two blocks, close or far from the window, because we think that's important due to the light impact. And every block is again split into two sub-blocks, either the two upper rows or the two lower rows, because there's four rows on a table, will go to a certain soil type. Because we remember that we said that we fear that bigger plants, because they are growing in fertile soil, they will be bigger. They will shade the smaller plants, and therefore even more affect the phytochrome A levels than soil alone. So that would be an indirect effect of soil fertility. So in each subblock we would have 10 pots, each pot one plant, and we had um, two leaf samples which were assessed separately for phytochrome A. So we're going to have on every single plant we're going to have two assessments. So how we go about it? First, we will define our design. I do this in R straight away, but you could do this as well in Excel if you would be more familiar with Excel, and then at a certain point import your design into R. I'll quickly show how I do it. So I have a data frame consisting of 120 pots for the time being, organized in 10 rows, in 10 columns, column 1 to 10, and in 12 rows. So if I view this, I get a data frame with pot 1, 2, 3, 4, and that goes on till 120. Yes, and we have columns and rows. So for each row, we have 10 pots in each column, and so on. I will not go through the R code in detail of how we assign all the rest, but it's rather simple. Depending on in which row you are or on which table you are, you will get another sub block. Yeah. I will make the code available through a markdown so you can look in detail how this works. Same thing, we set up the varieties. So this for every table, there's one variety, and the varieties are randomized. So because of this sample function here, we're gonna either take one of these three to go on table 1, and then another one on table 2, and another one on table 3. Nothing very exciting, and like I said, you could do that as well in Excel. I can also quickly give you a picture of how it looks like. So you see we have 10 columns. We have the three tables, and at this moment I'm showing you variety. So this is uniform for variety on one table. Okay, next thing is to attribute the soils. Yeah, and remember we would like to put one soil type in a subblock. And I'm going to show you the subblocks here the same way as I showed you the varieties. So you see we have smaller blocks of 10 pots, and so in each of those there should be one single soil type. So we have to assign 4 different soils to this table. Yeah, so again, this is the first table. Now, remark that if I assign to this pot here, I assign a soil type, for example, rich, then obviously this entire subblock will be all rich soils. Yeah, that's how we define it. But within that, so this subblock and this subblock go together in one block, I should have the other soil in the other subblock. So if I define that this is rich, I not only define this ones as rich, but I also fix that those ones will become poor. So if I fix this one, this entire block is determined. And if I would like to have the opposite happening in the second block on that table, and I want to reverse that order, I actually even fix this one and this one as well. Yeah. So by fixing, deciding on which pot this will be, I actually fix the entire table, which gives you problems with randomization. This is not very random, so you only have 2 options here to fill up this entire table. Yeah, and the same applies for the other tables. So we have a design which is not as random as we would like. And remember, in the first session we said that randomization is one of the cornerstones of experimental design. And we'll see how that will backfire on us later on. Okay. So again, I assign these soils. You see, there's only 3 sample moments, so it's yeah, not so much randomization going on. You can have a check how I do this in practice when you see the code in the R Markdown. I'm going to show you again what the result is, and you see, so this is a rich soil, a poor soil, a rich soil, a poor soil. I have the opposite design on the second table, and I have again the same design as on the first table. Yeah, so there's only three decision points to be taken here, so not, like I said, not very random. Okay, so now we have our design, and like I said, this step, if you don't like my R code so much, this is certainly something that you could do as well in Excel. And so our data frame greenhouse 1 looks very much like an Excel file that you could have organized yourself, 120 pots. Okay, now I start adding or going to the second step of the simulation process. It's simulating the response. And for this response, I work always with, for each factor that will be in my model eventually, or which will affect my my response, I have a thing called effect.soil or effect.variety or effect.block or effect.subblock. Yeah, and I will in the end add all these effects together to come up with the final Phytochrome A level. The first one, the important one, is obviously soil. There's only 2 cases: either your soil is rich or it's poor. And in our research question, which I repeated at the top here, we think that or we said we would like to have an experiment that is able to distinguish Phytochrome A levels that are 10 units different between poor and rich soils. And that's what I try to do also over here. I have rich soils have 100 units, whatever that unit may be, and poor soils have 10 units less, so 90. So that will be the estimates that we will try to reproduce in our modeling in the end. And then the rest are the famous variance components. So we have a variance components for variety, for blocks and subblocks, for the individual pots, and in the end for the two assessment on one pot. If you have a closer look at how I assign these variance components, then you see you will always find a term like this. So a random draw from a normal distribution with zero mean and a standard deviation of 10. Yeah, because we defined somewhere that the variance component for variety is 10. Yeah, and we're gonna take three draws, random draws from that population because we only have three varieties. Yeah, and these three numbers that we have, we're gonna actually. Okay, sorry for the interruption there. Something went wrong. So, like I said, three varieties. Each will have a random draw from variety, and I will assign one of these drawn effects to the slow, fast, and very fast variety. Okay. Wait a minute. I haven't done my first part. Yes. So slightly different ways, but for the rest, all very similar IDs on this R norm. You see zero mean and the variance component for block or for subblock, and will not. Individual plots is easy because every single individual plot needs a effect, because all individual plots are different. Usually differences between two plots are quite important, so I have here a rather large variance component. Yeah, so plots goes there. And then I have two assessments per pot. Until now, my greenhouse.1 data frame only contains 120 records, one for every pot. So in order to get two records for each pot, I have to double this data set. So I'm gonna bind two copies of the same thing together, and I'm gonna call one assessment 1 and the other one assessment 2. Okay, and I'm gonna add the random effect for assessment again in the usual way. Okay, so you see the variance component for assessment is quite small. And then eventually I will, all these individual effects, I will add up and put it into a new variable called PA for Phytochrome A. So again, we have a data frame that looks like this with the design factors that you know already, the individual effects of each of these variant components. We have assessment 1 and then assessment 2 later on. And now we have 240 records as we expected, and we have a value for our PA, the one that we were eventually art with. That's the one we try to simulate. So we are done with the simulation, and now we can do the modeling. I use LMR test, which is a variant of the LME4 that you've seen before. The only difference is that we gonna get p-values, while the normal LME4 doesn't provide p-values. For the rest, very similar. You see same function names and same syntax. I also have this one. Don't get worried about that. Um, Sorry, don't get worried about that. The reason is that I add some control terms to that modeling, but that's certainly not of importance at this moment. So I'm going to run the first model, which tries to model Phytochrome A with a fixed effect soil and then all the variance components. So variety table, block, subblock, and pot. I don't have assessment here because assessment is the lowest level, and by definition, the lowest level will go into the residual level of the variance components. So you don't have to call that explicitly. If I run this model, I have a little warning here, but have a look how it looks like. Um, and then it is the output that you're probably familiar with right now, with all the variance components here, and then here the fixed effects. Now, one thing that should catch your eye is that the variance component for table and variety are exactly the same. And this is not unexpected because remember, we deliberately confounded variety and table. We put one variety on a table. Yeah, we confounded these two factors completely. We want to keep the effect of table and variety in our in our um, in our decomposition of variance components. We but we're not interested in finding out which part is actually coming from a table and which part is coming from the variety, because we didn't have enough space to properly test each variety in an adequate way. Now, the consequence of not randomizing tables or varieties over tables is that you see there's something awkward here. Yeah. So you will have to make a choice for these completely confounded factors that you will have to drop one of those two, and variety or table have to go from the model, and which one of the two doesn't matter because they are anyhow exactly the same. Apparently, I choose to drop variety, but you could have chosen differently for your second model. Now I don't get any warning, which is already a good sign. And if I give you the summary of what it is, you see there's no variety left here. The other interesting part, or that needs our attention, is this fixed effects, because that's what we're doing the experiment for. So you see that the estimate in this case for the pore soil is extremely close to the 90 that we had put in our simulation exercise, and the estimate of the 10 is also very close. Yeah, so this is the difference between rich and poor soils. We have a standard error which is actually very small compared to this 10, and we have a highly significant effect. So in this case, with this simulated data, the experiment would have no problems at all in telling you that the difference between rich soils and poor soils is highly significant. So it would be, this experiment would be good for answering this question. So if we take this back to the explanations we give about why do we do simulations, so we have already a couple of questions answered. One is, do we have a model that works, and can we analyze it? And yes, we have one now. And apparently, at least on this simulation, we get estimates that are very close to what we put into the simulation engine, and also we have standard errors that are very small. We get p-values that are no doubt at all significant. So we have certainly a design that is also fit for answering our question, and not only technically analyzable, but probably also fit for the job. Yeah. We should take that a little further also in order to answer the next questions, like compare different alternatives, and therefore we will have to do a little bit more simulations in order to get a better view on whether what we got here was coincidence and we really got lucky with these nice results, or there's something that will, whatever data we simulate, that will be reproduced time after time. Okay, so we will have to automate things a little bit. Means also that we cannot work with this sort of output, so we will have to make up our mind what of this output we would like to have. I showed you already summary 2. Summary 2 coefficients gives you only the fixed effects here. Oops, sorry, only the fixed effects, which is exactly the same as what I said before. And in this case, the interesting part, I think, is how is this estimate and how is this p-value here. So I'm going to take on the second row element number 1 and element number 5. So that would be a nice way of extracting things. Now, another interesting thing to extract would be the confidence interval on this fixed effect. Yeah? And if I run this code that you know already from the markdowns, you see, don't worry about these ones. You see that I have the confidence interval on this soil R, and you'll see how I extract this part out of this these confidence intervals. Okay, so in order to easily simulate data, I'm gonna, the code that we have seen before, almost copy paste into a function, a shell of a function, yeah, simulate response and then a function and then all the code in there. The only thing I change is that eventually I return with the new data frame that I need, yeah? And I'm gonna put in arguments for the different variance components or effect sizes. Yeah. So instead of where I had 9 here, I am able to put in that effect into the in the function when I would call eventually simulate response. Same for the variance components for variety, block, subblock, plot, and measurement. Yeah. So that will allow me to quickly create lots of these simulated responses. So if I do a test, you see that I have a data frame. You see the first 6 lines of that data frame where I have this design with a PA. If I do that again, you should have a slightly different response. Yeah, see, the first one is now, and this you have some different numbers. So we are able to quickly generate lots of these responses for Phytochrome A. I do the same with my model. So the model you will recognize here. So the one without variety, again with this gibberish that you don't have to understand. Plus the extraction, yeah, and I have here the part on the confidence interval that you will recognize. I'm only looking for the fixed effects, and I'm only gonna take the second element of these fixed effects. So that's gonna give me where do I have it? Only gonna give me those lines here, yeah. So that's gonna give me 2 numbers. The lower bound and the upper bound of the confidence interval, and I split them further into 2. So what I return from this function is the lower bound of the confidence interval, so this first number here, the width of the confidence, so this one minus that one, so the width of the confidence interval, and then the fixed effects and the p-value I have there. Okay. Don't worry about this one also, because I in this function I added that I either want to have summary, which I need in my in my simulations, because I only want to work with very simple output, because otherwise I cannot manage it, or I would like to have the full model returned, which I could use for checking. But in this case, default summary is on true, so we will give the summary results of that model. So I define that as well, so we can see how it looks like. So I have simulated a response on that basic greenhouse 1. I extract the interesting bits from a model, and you see I have this lower bound of the confidence interval, the width of the confidence interval, the estimate, and the p-value for this model. Again, here everything seems to be nice, and very small p-value, an estimate rather close to the 10, and the lower bound of the confidence interval is clearly above 0, which is consistent with this small p-value. Okay, so once I am able to do this, I can repeat this many times, and that you do by the replicate function. I do this 500 times. In this case, it will take a while, but I will stop the video and call you back when it's done. Well, take a while, maybe 3-4 minutes, and I have exactly the same code as I had just before. But now I will do this 500 times and store it in a new object. So I run it and I stop my video. Okay, we are back. You see that we had so the whole function has run. It took 3-4 minutes. You see that on the 500 attempts we did, there's 3 cases where we had a slight problem with modeling, which is okay. I mean, 3 out of 500 is okay. That won't affect our results too much. So now I have a matrix that is built up of 4 rows and 500 columns. The 4 rows are for the 4 outputs that I would like. Yeah. So remember, the first one is the lower bound of the confidence interval. Second is the width of the confidence interval. The third one is the they are here, is the estimate, and the last one is the p-value. So with these numbers now we can try to summarize what they give over these 500 simulations. And for instance, the first one, the lower bound of the confidence interval, so number 1, yeah, that's gonna give me 500 numbers. So in order to summarize this a little bit more elegantly, I'm gonna take the quantiles, namely the 0.025th quantile, the 0.5 quantile, or the median, and the 0.95. So these 2 extremes here, what I took, will together give me a 95% confidence interval of something that is about confidence, a 95% confidence interval. So a bit confusing maybe, but if I run this, you see that hardly seldom, yeah, only in 2.5 of the cases, that lower bound of the confidence interval will come in the neighborhood of 0. And so that's where we will have troubles in seeing whether things are significant or not. Yeah. In general, this confidence interval is about is not on half of the cases. The lower confidence bound will not be lower than 6. Yeah? If we actually count how often we are actually below 0, then we see 498. So 498 out of 500 as a very small number. So it's only in 2 cases out of these 500 that we actually couldn't detect a significant difference. We could see that in another way and find out how often, the p-values is smaller than 5, and we would have to come in the neighborhood of this 498, I think. So 483. Um, so we could say that the power of this experiment to detect a significant difference of 10% is almost 79%, so very high. Right? You'll see probably you can do with a little less, because to get to these high powers, you actually have to make experiments that are probably a little bit too big and very expensive for the sort of thing that you would like to show. So you probably can diminish your cost by making a smaller example and still have reasonable powers. Um, let's see how the width of that the confidence interval is, and you see that the width is well, on average around 8. It can sometimes it is better, sometimes it goes up to 13. Yeah. Um, and the actual estimates to see if there's no bias in our experiment, you see that 50% is exactly on 10, or very close to the 10 that we put in our simulation, and but sometimes it goes as low as 5.6, and sometimes it goes as high as 14.5. Yeah. Okay, so the conclusion of our simulation is that in 97, it is actually 97% of the cases that if the real effect is 10, and we guessed the variance component uh, not too optimistically, um, we would have a clear answer from this experiment. Yeah, so that's in that sense a good experiment. It may be a little bit overpowered. Now, and therefore, with that we come to the last step of the simulation, or the reasons why we do simulations. Can we compare alternative designs? And that's actually why we're doing this whole entire exercise. Yeah, because we will probably not be able to come up with the perfect design by just staring at schedules or schemas of pots scattered in a greenhouse. The reason why we're doing this is to come up with different alternatives and compare how they do. And so, because we found out that actually we have lots of power, and we could try to save some money by making the experiment smaller. And then the first thing I would come up with is to, instead of having those two assessments of this Phytochrome, which is probably a rather expensive and laborious task to assess all these 240 samples, you could say, well, what if I would have only one assessment? So if I throw away half of my assessments in my previous data set, and do the model again. Yeah? So that's what I'm doing here. I'm throwing away half of the assessment. I'm throwing away assessment 2 actually. I have to adapt the model a little bit, because now my lowest level is pot. It's not assessment anymore, so I have to remove pot from my model. So I have a slightly different model, and it still works. Yeah? I can show you how it looks like. Nothing uh, interesting. The pot is gone here now, but we still have a estimate that is very close to what we think it should be. Standard errors are still very small compared to that estimate, and we still have a very significant value. So in this case, with this data set, we would be fine with only one assessment. So what do we do? Obviously, we're gonna put this new model again in a similar scheme as what we had before. Um, and I'm gonna do the simulations again 500 simulations, but with only assessment 1. And I run and I'll be back in 4 minutes. Okay, our model has run. Um, okay, you see again 2 failures on 500, so that's okay. And let's see how we did. So if we look at the lower bounds, you see that also here, even with only one assessment, we hardly never will have a lower bound smaller than 0. If we go for the power, we still have a power of 482 divided by 500 of 69, yeah? 96, sorry. Um, so there's still ample of power even if we drop um, one assessment. Yeah. So you I hope that you start seeing the advantages of mm, doing the simulations properly. It allows you with, yeah, I don't say a little bit of effort. I mean, it's probably certainly when you're not so familiar with R, it is it can be quite some effort, but once you know very well how, or very well, or you have a good estimate of how your variance components are, what sort of variability is coming from which source, and you're doing the simulations, um, which is basically all work that you can do from behind your computer, uh, or by asking somebody to do it for you, you actually are able to save half of your lab work here, yeah, with no consequences at all. Yeah, so you have an equal amount of power than you had before. Yeah, so no problem at all to take only one sample. I hope that makes clear that you can do enormous savings by going through this sort of exercises. Now, a second example that I would like to add here, or I don't know if it's second or next example, it's to go radically for another design. Remember that we said, and the picture is still here on the side here, is that we had some yeah doubts about whether we had been randomizing enough. Yeah. So suppose that we think, wow, these plants are not that big when we sample them, so probably the problem of shading is very limited. So instead of having these big blocks of 10 pots, we're gonna have smaller blocks of 4. Yeah, and we're gonna have uh, on one table 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then a smaller block, and so it's going to be unequally sized blocks. Um, is that correct? No, we're going to have 1, 2, 3, 4, 5. 5 blocks times 5 is 10, so we're going to have still equally sized blocks. Um, but it's going to be much more room for randomization, and actually I even don't control anymore where um, where where the soils go to. Um, I'll show you how it looks like in the end. So I randomly let choose where these things go, and because I have so many of them, I have um, uh, oh, here I'm. So in this case, you could say, not such a good choice. Yeah. So I could repeat my design because my random assignments happen to be not random at all. So that's what you can have with random assignments, that by coincidence you don't have randomization at all. Yeah. So that's why we normally help things a little bit. Okay, never mind. Um, let's do this on these smaller blocks, the same analysis as we done before. Um, and because we already thought that the second assessment doesn't help us, I also immediately gonna drop that second assessment. So I'm doing a next run. Gonna take me again 30 minutes, sorry, 3 minutes. So I'm gonna stop the video over here. Okay, model has run. Now we have 6 problem cases out of 500, still nothing to worry about. So I'm going to compare this design with the previous one where we also have just one assessment. And what I'm going to compare now is, for instance, this width of the quantiles. Yeah. So the quantiles, sorry, the width of the confidence intervals by showing you the quantiles. So the width of the confidence interval is on average about 7 in this design. While it can, in really good cases, it can go down to 5.4. In the bad cases, it goes up to 9.3 and a half. 9.336. If I compare, if I do the same thing for the previous one, so the greenhouse one, but also with only assessment one, you see that on average, confidence intervals are slightly bigger, which is a bad thing, but that difference is not bad. On the lower end, you will not get any better, of course. You will have slightly higher as well, but it's mainly on the high side that once in a while you're gonna have very wide intervals. So you're gonna have sometimes intervals which are quite wider in this first design. So what is the difference between those two? It's the size of the blocks and is the amount of observations or amount of sub-blocks we have and the degrees of freedom that go with it and the possibilities to randomize there, because we have randomization. And again, in this case, it's not too dramatic because we are already in experiments that are highly powered, yeah, still too high powered according to my taste, and therefore the impact will not be so high over here. Yeah, it is already considerable, but it's not dramatic. Also, the second or also this design was good enough to show the difference that we would like to see, but that is just because it is, yeah, it's that big. Yeah. So if you would get into smaller experiments, taking care of this randomization and the number of observations that you would have would be becoming much more important. And I hope you see this by those two experiments. So having, although the things are not very random in the end, yeah, but because I allowed randomization, because I have much smaller subblocks, I get a more powerful experiment. So it will be again your knowledge of the subject to decide: do I uh, am I really worried about this shading effect, and do I need bigger blocks, or can I get away with smaller blocks? I don't fear that shading effect, and that will give me a better design. Okay, I hope that made again a couple of things clear.